Hello, my peeps. So we're going to go ahead and continue on with in chapter 2, section 2.4, and talk about a sort of relationship between limits and derivatives. We talked about this issue in pre-calculus, but I think that everyone definitely needs a good reminder of this, especially because it kind of sets the foundation for what we're going to be doing for the majority of the first semester as is. When talking about limits and derivatives, what we really are talking about is a problem associated with slope. And so I'm just going to remind you of this problem which we've dealt with. And of course, I'm going to accompany it with my wonderful graphs and handwriting. Let's just say we've got some random graph, some random function we want to look at. Let's say we've got 2 points, A and F of A, and let's say B and F of B. Of course, I'm being just as creative as I always am. Let's just say that this function looks something like this. And of course, I've labeled this f of x. And so we've just got some function with 2 points on it. There we go. So in the past, we talked about sort of calculating slopes, finding slopes, etc. And we noted that if we were to try and find, let's say, an average slope in between A and B, that would be something that we could do, right? Finding an average slope is something that we've been able to do, hopefully, since somewhere around Algebra 1. An average slope on this graph, ooh, that's not a bad line. I screwed it up at the end. Would look something like this, right? We've got a slope that's going through 2 different points, and an average slope is always represented by the same slope equation that we've been using since Algebra 1, which is m equals, and you might have seen it as y2 minus y1 over x2 minus x1. That's, of course, the exact same thing as, right, rise over run, or whatever you want to think about it as. But we changed it a little bit when we started talking about functions other than lines, right? So lines always have one single slope, and they're always just the subtraction of 2 y values, 2 x values on that particular line. But when we look at other functions, right, we note that the slope of other functions changes depending on what point you happen to be looking at. The slope here on the function is different than up here, which is different from over here. And if we allowed this function to continue both directions to negative infinity and infinity, it would be different all over the place. And so we modify our slope equation to look something like this instead. So instead of y values, we've got f of b minus f of a, and then on the bottom, b minus a. There's still y values, but they're specific values that are part of this function. This equation here, m equals f of b minus f of a over b minus a, will always represent the line that's going through 2 points on the graph. And we state that this type of line, which is going through 2 points on the graph, is called a secant line, right? So we've often labeled this as m secant, or the slope of a secant line. And you can write that out if you need to write that out. But the point is that finding an average slope involves finding the slope of a secant line, and specifically finding f of b minus f of a over b minus a, right? And so this slope tells you things, right? It tells you about the rate of change of the graph. So in this case, our rate of change would be positive, right? You can see that this line is going up. So overall, from A to B, we would state that we're going up. But we also recognize that this type of situation, that is modeling slope over a large interval like this, doesn't necessarily give us the best representation of all the slopes in between. And so because of that, we sort of had this hypothetical thought process that we talked about. And that thought process was something like this. Like, for instance, if we wanted to find the specific slope at, let's say, A, which I'm going to label like so, with this little pink line here. Clearly that pink slope is not the same as the blue slope. And further, we might say that the blue slope is a poor approximation of the pink slope. And our thought process was, well, if these 2 points were a little bit closer together, right? Like if I were to have drawn my secant line like this, right? Or maybe I should use a different color for my approximations. Like if I were to draw my secant line a little bit closer, right? Like that, that's a little bit better. Or maybe if I draw a secant line like that, that's a little bit closer. If I draw a secant line like that, That's a little bit closer. Clearly, the closer that I get to being actually at the point a comma f of a, the better approximation the secant line is to my pink, what is actually a tangent line here, right? That's the idea, right? We want to push these closer and closer and closer. And so in order to actually push those closer, right, we essentially utilized what? Well, we utilized a limit, right? And to show you the two forms of that, I'm going to change up my axis a little bit. I just wanted to sort of define the problem for now. So let's go ahead and do that really quick. The first way that I think we actually changed this axis was I think we used a definition with x's and c's, if I'm right. So in other words, we had on our axis some value c, some value x, and then we had maybe a point here and a point here, and we stated that this was f of c, and we stated that this was f of x, and we drew ourselves, once again, some function, if I'm correct about that. And the idea was, well, I'd really like to, for instance, generate a line that represents the slope at c, but I'd like to do so with the idea that at the moment I can only generate a secant line in between x and c. So this is the same type of problem. I've just changed up the notation to allow us to generate a specific definition. So we stated, right, that the secant line's slope would be equal to f of b minus f of a over b minus a, right? And in this case, our secant line, our f of b minus f of a over b minus a, well, that's going to be specifically, right, we've got a point here, x comma f of x, and we've got a point down here, c comma f of c. So here's my y2, my y1, my x2, my x1. If we plug that stuff in, that's going to give us f of x minus f of c, and then on the bottom, x minus c, right? Here's my slope of my secant line. Now, that said, the issue is that that's not a very accurate approximation of this sort of magenta line over here, my tangent line. And so I'm going to use that thought process before, which is that if I move these approximations closer and closer, right, that's the idea. And I just did this, but I'll just quickly make a couple. If I move this closer to here, if I move this closer to here, that'd be good. And as I always have concluded with my students, like if I can make this distance so small that it's essentially zero, that would give me the best approximation. Like if it's right next to it, like that's still pretty good, but it'd be really great if we could make it non-existent, which seems like it's not probable, or possible, but mathematically it is possible. And specifically, oh, I guess I didn't finish my thing over here. Sorry about that. Mathematically, it is possible, and it's possible by using the idea of a limit. In other words, we can force our x value to approach c. So we could state that the limit as x approaches c of this expression or of this slope could be true. And this would ultimately define the slope of this tangent line, what I have here in magenta. So the concept of a limit here is allowing us to force x, right, here's x, to approach c or get closer and closer to c until it essentially hits c, right? And you can see that, quote, essentially hitting c occurring here in the denominator, whereas if we were to solve this limit directly, we'd have c minus c, which is 0. In other words, the distance between x and c would be 0. Now, this specific situation here is, of course, at the moment unsolvable, but as we've seen in the past, it's quite easily solvable using either algebraic methods or other methods. And so there's sort of our conclusion, our solution to this issue so far. Now, we've talked about this in the past, but I've never sort of put a name to it. And I do want to put a name to it right now, and that name is going to be the second definition, right, of a derivative. And we used this second definition rather than the first definition for a while because it's easier to solve when you have a specific point on the graph, which is all I really give you in pre-calculus. I don't really give you any sort of differentiation problems yet. So we're going to just label this as the second definition of a derivative. And for the moment, what I really want you to take away from this is simply that the slope of a tangent line is equal to, right, the derivative. That's what I want you to take away from it right now. Now, this is the second definition of a derivative. Often, however, we use the first definition of a derivative, which we need to look at. It involves the exact same sort of system of proof, but the formula that you get is a little bit different and sometimes is more helpful, especially when you're calculating the derivative of a function generally or differentiating a function rather than finding a specific value. So let's just quickly draw this out and go through the thought process just one more time. I do think it's worth it to go through this a few times anyway, because I think that this theory is really necessary for us to understand what's going on. But let's say I have x as a value and x plus h, right? So x plus some value or plus some distance h. This y value would be f of x. This y value would be f of x plus h, right? Same exact sort of situation. We've got some function that's going up. We've got some theoretical secant line, which is going through these. That wasn't too bad. Not the worst, not the best. And then we realistically would like to find, I'm going to use orange this time, the slope of this tangent line that's supposed to be hitting x, but isn't because I'm not the greatest of drawers, right there. So once again, we state that the slope of a secant line is, of course, f of b minus f of a over b minus a. That's the average slope. In this case, we've got specific points though, right? We've got here at this point something x plus h, and then f of x plus h. Down here we have x and f of x, right? These are just two random points on the graph. Let's go ahead and plug those in to make this more specific then. So f of b minus f of a is going to be f of x plus h minus f of x. And then on the bottom, we've got x plus h minus x, right? y2 minus y1, x2 minus x1. If this gets simplified down just a bit, we've now got the slope of the secant line as f of x plus h minus f of x. And notice the x's here are going to cancel in the subtraction, so we're just going to be left with an h in the denominator, which is what makes this definition a little bit different. And notice that what we have now is slope of a secant line. Ideally, we want to find the slope of the tangent line, right? So we want the slope of the tangent line. And if you notice in the last example, what we wanted to do was essentially make x approach c, right? Notice x approach c. This is not the exact same situation, right? We could make x plus h approach x, right? But because our value here, our slope of a secant line is a little bit different, notice that what we actually care about here is something a little different. What we care to do in this circumstance is to eliminate the distance h. Notice that to get from x to x plus h, I have to plus h, right? I have to add h on, that amount of distance. And so ideally, in order to make this tangent line or get the best approximation, remember we're getting closer and closer and closer, what I want to do is I want to eliminate all this distance h, right? In other words, I want h to be essentially approaching 0. So for this limit, or my slope of the tangent line over here, what I'm going to do is I'm going to force h to approach 0. I want the limit as h approaches 0. So this distance going to 0. And then I want that obviously to apply to this slope equation, because I once again am finding the slope of this tangent line, and that's what I'm trying to accomplish here. And so we get this slightly different version of the same sort of proof. Notice this is the limit as h approaches 0 of f of x plus h minus f of x over h, whereas in the last case, it was the limit as x approaches c of f of x minus f of c over x minus c. The limits look a little different. They accomplish similar things, but they do look different, and they're necessary to pay attention to. They function a little bit differently, and later we'll see how there's a bit of a difference in what definition we might use depending on the type of circumstance given to us at the time. So I'm not going to go any further for now. I just want to put that out there for this next assignment, because there's a couple different problems which you'll be sort of useful for you to go about doing. But for the moment, I want to stop there, I think. I think the only thing that you really need to recognize when doing the homework is what you're looking at. So if they list a limit that looks something like this, you need to recognize that what they're giving you is a derivative. So once again, slope of a tangent line is equal to a derivative. And this specific one is the first definition of a derivative. When we start differentiation properly, the next chapter, we'll talk more about this as well as what it looks like in practice.